Okay, only a few more chapters left, so we're at chapter 12, and we're talking today about inferences for population proportions. So, in here, we have to talk a little bit about the binomial distribution because a proportion is basically a yes or no question, similar to what we did back in when we were talking about binomially distributed random variables. So, that's exactly what we're doing here. So we have a two-answer format. So yes or no, true or false, male, female, whatever we're looking at. We're looking at a binomial distribution. So our population proportion, so this is the proportion of yeses or successes or whatever you want to call it. We call them P, or we can call it prop. That's our population proportion. Then we have a sample proportion. So that's denoted by P with a hat. I call it P hat. You'll hear me say that all the time. That's the success proportion for our sample. So basically we say X, which this X right here is actually, that would be our binomial X. The number of successes. Just like we did in binomial. And basically what we're doing is this P hat becomes kind of a scaled binomial because we just divide by n, the sample size. And so at this point, we now have our P hat, and this is what we're going to be dealing with. This is our sample proportion. So how many vehicles in Alaska are SUVs? A lot, actually. And we might want to make some sort of inference about the proportion of SUVs in Alaska versus the proportion of SUVs in the entire United States, for example. So this may be something that we might want to do with this. So, of course, every sample statistic, including P hat, has its own sampling distribution. So now, instead of talking about sample means, we're talking about sample proportions having their very own distribution. And the mean of our P hat is our true P, our population proportion. So this becomes almost normal, and here's skipping ahead a little bit. The central limit theorem you can use a normal approximation of your binomial, and this can be P hat. So with the mean being P, and here's your standard deviation. The standard deviation of P hat, or the standard error of P hat, because remember, a standard deviation of a statistic, a sample statistic, is called the standard error. And this is what it looks like, P times 1 minus P divided by N. So now instead of NP times 1 minus P, remember, we scaled this down, so now it's divided by P. So, according to the central limit theorem, P hat will be approximately normal as long as we have sufficiently large N. Okay, forget what you know about 30. That was our rule of thumb for means, but when we're going to make inferences about proportion, we need to change that. It's no longer about the means. It depends on the P or the P hat, depending on if we have a P or not. And that's depending on if we do a confidence interval or a hypothesis test. So if our P or P hat is near 0.5, then remember, if this is close to 0.5, this will be very symmetrical. Near 0.5 means my binomial distribution is nearly symmetrical. So we don't have to worry quite as much of what n is. But if it's 0.01 or 0.99, Remember, if it's 0.01, that's way less than 0.5. That's going to be severely skewed right. This one's going to be severely skewed left. So we have a little bit of a problem because we have to have a large enough n to pull this over to being normal. So here's a rule of thumb. Both of these have to be true. The n times p, and that's the hypothesized p, right, has to be greater than or equal to 5, or if we don't have a hypothesized p, then np hat is greater than or equal to 5, and n times 1 minus p has to be greater than or equal to 5. Or again, if we don't have a hypothesized p, then n times 1 minus p hat is greater than or equal to 5. So basically, these over here, you can also say the x, so the number of successes has to be more than 5, and the number of failures has to be more than 5. So now let's move on to the confidence interval. If we want to find a confidence interval for the true proportion, then our formula looks just like this. Now notice we're a little bit different here. We go p hat plus or minus the z at alpha over 2. Remember, this is the z equaling, it's either going to be 1.645, 1.96, or 2.576, depending on if I have a 90, a 95, or a 99% confidence interval. Okay, so that's what the z is going to be. And now look, I don't have a p naught, so I have to just use p hat in there. So it is going to be a little bit different. And when we do our assumptions, of course, we just have to make sure that x and n minus x are both greater than 5. Okay, so let's use our calculator to do this as well. Now, again, our assumptions, we go to 1 prop zn. This is very simple. You just put in the number of successes, the sample size, the confidence level, and hit calculate, and you're ready to go. Okay, and the output is just going to give you your confidence interval, your p hat, and your n. So what is the 95% confidence interval for the proportion of students at UAA who are Native Alaskan? So let's remind ourselves really quick. We had x was 31, n was 245, and that's really all we have and all we need. And then our C level, of course, is 95%. So let's go over here. We go, I keep wanting to go to distributions for some reason. I think I'm used to it. Okay, so we go here. Now we want to go down to the interval. So you have to make sure it says interval. 1 prop z int. So it's a 1 prop z int. And what's really nice about those of you who have the 84s is it actually keeps in just the last thing that you did, even if it was a 1 prop z test. And so you have x is 31, n is 245, your C level is 95. So you're going to hit calculate, and you find out that 0.0849 to 0.16816, and we are, and you can say it like this also, the way that I've been writing them in class also, is our p is between these 2 points. So we are 95% confident the true, and make sure you write the word proportion of Alaska Native students at UAA is between, and you can even turn these into a percentage now, 8.49% and 16.82%. Now you'll notice that this also gives me the same conclusion that I drew in my test, because remember, the state of Alaska is 15.6% native. Is 15.6% contained in this interval? Yes. So it is possible that the UAA students are 15.6% native because that's within our 95% confidence interval. And you'll also notice it gave you the p hat and it gave you the n as well. 0.127, yeah. And n was 245. Okay, so let's move on to the next thing we want to talk about. If it'll move on me, and it won't right now. Okay, got it to work. Magic of the pause button. So, remember, margin of error, I like to call that ME anyway, is Z times P hat, 1 minus P hat over N, with a square root. And so it's also half the length of your confidence interval. Remember, you can take your upper bound minus your lower bound, then divide by 2. So you can actually find your margin of error that way. So if we are given, so now let's say that we are given a needed margin of error, and we need to find a sample size. I said it. We need to find a sample size. Now rearranging this thing gives me this guy right here. N equals, excuse me, P hat times 1 minus P hat times, or Z over E, and all of that squared. However, if we haven't taken the sample yet, I don't have a sample proportion, so I don't have a P hat. So I go, wait a minute, I don't even have a P hat, so how am I supposed to figure out an N? Well, one of the things we can do is we can figure out, well, what is the highest number that P times 1 minus P can actually be? And here's getting into just a bit of algebra, but if we have P minus P squared, that's what P times 1 minus P is. I just distributed the P. If I graph this, it's going to be a parabola, right? P times 1 minus P. And it's a parabola that's going from 0 to 1. Because P is always less than 1, right? So this is the only places it's going to go. P has to be between 0 and 1, so this is the only place P is going to go. This is P, and then this is P minus P squared on the y-axis. Now look at this. This maxes out at 0.5. But what value is this at 0.5? Well, 0.5 times 1 minus 0.5 is 0.5 times 0.5, which is 0.25. So the highest that this number can ever be is 0.25. That's that maxes out there. Because if I'm over here at 0.4, well, 0.4 times 0.6 is 0.24. That's right here. If I'm at 0.3, 0.3 times 0.7 is 0.21. You see what I mean? It goes up. But then if I'm at 0.6, it's 0.6 times 0.4 again. So it's going back down. So the highest it can be is 0.25. So when we don't know anything about P, we're just going to call P times 1 minus P 0.25. And of course, you have to round up again. But this will give me the sample size needed for a margin of error of at most E. Now, it may be smaller. I may get an even better margin of error if my number is not that high. So, back to our example. I want to estimate the proportion of UAA students who are native with a margin of error of at most 3 percentage points. What sample do I need? So I'm going to not assume anything about P. Now, if I want to assume something about P, if I assume that P, the highest P can be is 0.3, then I wouldn't use 0.25, but I'm not going to assume anything about P. So my N is 0.25 times Z over e squared. And I didn't say what I wanted, so I'm going to assume that I still want a 95% confidence interval. And the e that I want is 3. So n is equal to 0.25 times, and my z with the 95% is, you should be saying 1.96, I hope, over 3 squared. So I'm going to go 1.96 divided by 3, square that number, and then multiply by 0.25. Oh, that didn't work, did it? Did I do it right? Oh, 3 percentage points. Terry, I should have done that right. 0.03. Okay, that works. 3 percentage points, which is 0.03, right? I see what I did now. 1.96. Let's do this right this time. Divided by 0.03 equals, ooh, big number. Square that. Multiply by 0.25. That'll get a little better. And the answer is 1067.1. Round that up to 1068. So I inadvertently, yeah, I did that on purpose, right? I'm not going to retape this, so but I'm going to keep it because I think I just showed you guys a really good way not to make the mistake. Because if it says 3 percentage points, remember that means my error is actually 0.03. So it's really important that you guys do that. And again, even though this is 0.1, you still have to round up. So it's actually 1,068 students that I would have to poll in order to get this small of an error, margin of error.